Dr. Matthew Graham is a research professor of astronomy here at Caltech. His work focuses on the application of advanced computer science and statistic methodologies to data-intensive science problems. And he's particularly been involved in the development of the virtual observatory and its associated efforts and the statistical characterization of large sky surveys. So Matthew's talk today will be an introduction to time series analysis.
I'm going to give an overview, fairly high level, I hope, just broadly on time series analysis, sort of following on from what Kiri was talking about. Time series analysis and actually looking for really odd things in the sky is possibly the oldest application of astronomy or data science or whatever you want to call it. This is an anomalous observation from about 184 BC, and people have then done detailed analysis on it and characterized it and said, oh, something went up strange in the sky and that means something terrible is going to happen. So whilst astronomy was astrology for many thousands of years, we were still doing the sort of things that this sort of whole thing we've been talking about this morning is looking for. We're looking for the things that are weird. The first astronomical time series is probably British. It was a few months before Galileo discovered it. I'm sure Pepe will debate this, but the first recorded astronomical time series observations by Thomas Harriot of the moons. But this begins to get the idea of what we're talking about when we talk about time series and for the purpose of astronomy. We're looking at things in the sky, we're trying to put the data together and understand what's going on. But even then, the first variable star is Mira, discovered in the late 1500s, early 1600s, sort of 40 years of observations to figure out that this thing actually had a period of about 350 days. And the reason was the mindset then was that if the new star were outside the ordinary course of nature, it would tell us little about the constitution of the universe. Back in those days, they thought there was a very static model of the universe, the crystal spheres, all that, even though it was sort of 100, 200 years after Copernicus. And if there's something new there, it'll be a little bit interesting, but it's not going to tell us something significant about what's going on. That has significantly changed in the last 30 years, 20 years. We are now very much in the era of time domain astronomy with a whole slew of surveys going on, producing data across electromagnetic wave bands and into more exotic phenomena with gravitational waves and neutrino stuff. A lot of this George was talking about. Here, particularly at Caltech, the Zwicky transient facility. I should know that because I'm the project scientist. That's a mistake. Producing data, putting out millions of alerts a night of things that are changing in the sky and moving into that LSST era. So we now have probably on spinning disk and accessible to large amounts of the astronomy community, if not all the astronomy community, maybe about 1 billion time series across the sky in the optical and some in the radio, some in X-ray, etc., giving us all sorts of information. And so the question is, what do we ask of this time series? And I would say there are sort of 3 things that we are interested in when we do time series analysis. Firstly, we're interested in, with very large data sets, we can now do these population behaviors. We can sort of characterize these, figure out what the classes are, or characterize them, categorize them, and then classify them. Figure out what the things are and say, what does the population of stars of class X do in terms of how we can classify that. We're interested in the outliers, the stuff that Kiri was talking about. These are the extreme sources. These may tell us all the data artifacts we missed when we were doing our original pipeline processing, or they may be hints to new and exciting physics. And then maybe we actually have physical models of what we believe phenomenology may be going on. We believe there's some sort of object and it behaves in such a way, and we can make a prediction of what it's going to do. And because we're looking at the sky so often now with so many things, we can say, oh, we expect it's going to do this. So let's go and look at it in 2 weeks' time when we think it may be doing something interesting. And that's a sort of new thing that this wealth of data and the models and the analysis we do are applying to it. But in terms of the sort of things we see, this is Kepler data. This is just the source of phenomenology you see in young stellar objects. So we're not talking about just one type of pattern of behavior. This is work that Lynn Hillenbrand and Anne-Marie Cody here did last year. So you've got periodic, multi-periodic, quasi-periodic, bursting, these what they called aperiodic dippers, quasi-periodic dippers, stochastic, long time scale, all sorts of things going on. And even though those are sort of, it looks like that type classifiers, we can be a little more systematic in our analysis, and we can try and sort of break these down into the different class of astronomical variability. This is a 10-year-old diagram by Laurent Ayer of the so-called variability tree. Most of these are periodic variables. There are a couple of non-periodic ones, sort of AGN, and a couple of the stellar phenomena. We maybe have about 500 classes of different types of stellar variability that we've classified so far on the basis of time series, some to greater resolution than others, microlensing versus eclipsing versus cataclysmic versus pulsating. All based on these sort of analysis that we do of these time series. Are there more classes under here that we're missing? Are there classes here that would stand out very obviously as, artificial in some manner relative to what we think we understand as being the source of phenomenology that we see in the actual universe? So that's the sort of area that we are inhabiting, looking at the astronomical data. So let's get down to some nitty-gritties about time series themselves. So when we're talking about time series in astronomy or more broadly, we're thinking we've got a set of time-tagged measurements of something associated with observation errors. And these data objects are quite different from spatial data objects or other things we may be assuming with. Firstly, from a statistical point of view or perspective, the data it's non-independent and identically distributed because it's sequential data. So the value that I measure now or maybe dependent on the value I measured yesterday. If I'm thinking of a weather time series, for example, the probability that it's going to rain today is dependent some ways on the probability that it rained yesterday, or the fact that it rained last night means it may rain tonight, which is not good news if you're an astronomer, but so we have to have that notion when we're looking at these as for doing numerical analysis on them. We assume largely that a lot of our errors are drawn from the same process, these observation errors. This is called homoscedasticity. In astronomy, that's not often the case. If I take an observation tonight, the atmospheric conditions are going to be very different from the atmospheric conditions which were last night if I'd got an observation. The transparency might be different, the lunar phase may be different, the seeing may be different, all sorts of things. Even if I'm taking the data with the same instrument, it means that my observations, the observation errors, will be drawn probably from a different Gaussian distribution than what I did last night. So we assume in a lot of the analysis that we do that we're working with homoscedastic errors, but in time series, particularly astronomical, you're looking at heteroscedastic. There's this assumption that time series are stationary, that the generating distribution is time independent. That means that my mean doesn't change. But we know there are astronomical sources, such as the microquasar GSR 1915, which has at least 20 different variable states that have been identified. These are just 12 of them, and these are coherent states that you will see at different stages in the activity of this particular star, particular object. It'll jump from this state to this state to this state to this state, or randomly between different states. there are time series models where the variance is a stochastic function of time. So you cannot assume that what we're looking at is stationary. And it's not necessarily true that non-stationary time series have to be stationary in any statistical limit. You can assume weak stationarity, but it's not necessarily true. There's also this concept called ergodicity, which means that if we assume that our time series are ergodic, then instead of having to look at 10,000 one day, I can look at 10,000 day. That the time average of one sequence is the same as the ensemble average. This is the basis of we can look at phenomena of a large number of objects for a short time and infer something about the population or the behaviors overall. So these are some of the inherent assumptions that we make when we're doing time series analysis. And you have to be aware of them because the types of analysis or the types of objects you're looking at may not necessarily fall into those criteria. Sampling, very important one. You go over to the library, the science library here, or just around the corner, and you look at time series analysis literature, and 95% of the books will be on regular sampling, where you've assumed everything is day, if I want to sample the stock market, I'm going to look at the closing prices of the Dow Jones index, and that gives me something which is very regular. Our data are not regular, well, at least not from the ground, because we have weather, we have objects, we have daytime, we have objects you can't see for 6 months, etc. So astronomical time series are irregular, and there's a much smaller body of literature on that. Another thing that we talk about, ultimately what we want to do is calculate the power spectrum or the power spectral density of our time series, because that will tell us everything. That will tell us for a given frequency or for a different time scale, how much contribution there is to the overall variability of the object from that time scale, and we could then associate that with physical processes or whatever. But this is hard to calculate, particularly when you've got irregular sampling, so we do things like use the autocorrelation function instead, and if we're even lazier, we might use something like the structure function, and we can relate the two because that's easily quantifiable and you can relate them. So there's this notion when you start looking at time series analysis of the power spectrum of the process that you're ultimately interested in, because you believe that most of the physics will be there somehow, and that will give you insight into what you're actually looking at. There's also a notion that, well, there are two types of processes that may be present in what's driving the time series that I'm looking at. And there's a thing called Wald's theorem, which says that if I've got a stationary time series, or a stationary process, I can construct it into a combination of a deterministic process and some sort of stochastic component. And, GSR 1915, you can do the analysis and say those processes are coming from the deterministic, even if it's chaotic behaviors, and those processes, that behavior is coming from something that's completely stochastic. So it may be that when we look at given specific time series, that we have to determine which one's which, and that can again tell us what's going on underneath. So a lot of the background, the practicalities, however, as been said by George and Kiri, is that what we actually do when we come to the real data is we're aware of all those assumptions, but we do something which is more tractable, especially computationally. So instead of taking the power spectrum of this, which would be horrible, we substitute characterizing features. And we then project these into some sort of high-dimensional parameter space and look for anomalies or behaviors in that. Common statistical features, well, you can go to the literature, and as George said, there are about 60 or 70 that have been used. A lot of them have been selected for the purposes of computational ease, which is a bit surprising because we've got about 100, 200 years of physics knowledge and astronomy, and maybe we can come up with better ideas of, we're looking for physical processes that may manifest in this particular manner, and so why don't we look for those instead of just measuring flux ratios or the variance? But there are all sorts of things. I'll talk more about timescales in a minute, variability measures, morphology, trends, you can fit models and look for amplitudes between them, and this will give you a very rich feature space. It'll also give you a high degree of correlation between a lot of these features. We're very good at throwing a lot of the features which are capturing the same information, and then, you know, we really should reduce that down to, and there has been some work on feature relevance and that sort of thing, on reducing that down. What we can do then is we can take our time series and we can project it into some of these spaces, and that can help us do some sort of identifications. Again, in Anne-Marie and Lynn's work, they took these two features about measuring some sort of degree of quasi-periodicity against flux asymmetry, and then they can characterize, divide up their feature space in terms of those types of behavioral things they were seeing. So all the stochastic ones are over here, not quasi-periodic at all, and with a sort of no flux asymmetry. Again, you can look at timescales and do the same sort of thing, and you're looking for clusters potentially that are linked to the same sort of physics going underneath when you're doing this feature representation. You can do it with quasars as well, characteristic timescales. So these are stochastic variables. They're not, you know, less periodic, and you can tie it into different physics going on and things like that. Let's see, where are we? I can do, as Kiri was saying, maybe I'm not happy about the classes I want to do. I can do a clustering or an unsupervised learning exercise. This is from the Atlas catalog of stellar variables, and they've sort of defined classes broadly on whether it's, you know, high amplitude, long period, or pulsating or noisy sine curve or something like that. So they're more on, again, on the phenomenology of what they're seeing in the time series and less on maybe what the physics underneath it is. I mean, they're tying these then into some of those known classes, but what they've done here is far more of that sort of clustered, unsupervised learning analysis of the time series. So when you do this, and feature relevance, not all of those features are useful, and there are a number of papers which have done this, and you see always there's this very strong feature here, and what it turns out is that, of course, going back to that variability tree, and I said most of those classes are periodic, it turns out that the most important feature that is done is in a lot of these analyses that we've done so far with astronomical time series is periodicity. So we sort of assume this, and there's a whole slew of algorithms for finding periods in astronomical time series. You can do Lom-Scargill, where you're doing a least squares fit of a sinusoidal basis set to your data, and then comparing it to what it would look like against a white noise process. Or you can vary that and do it with wavelets or with spline functions or some sort of thing. Or alternatively, you can go non-parametric, and you can say, I'm going to guess an answer for what the period is, I'm going to phase fold it, and then I'm going to look at some metric of scatter, what my time series looks like in that phase folded version of itself, and then I'm similarly going to plot that characterizing statistic against the frequency I've done and see what it looks like. So this is one of those time series George showed. This is the variogram from a particular characterizing statistic here, and you see there's a lot of noise, but there's a minimum in this particular case. And when you phase fold this at that period, you get this in the phase folded, and that's what we call the true period. As I say, there's a vast body of literature in astronomy on ways of finding this. You can do Lom-Scargill, you can do these minimized dispersion measures in phase space, you can do rank ordering, you can go into Bayesian or neural networks or convolved algorithms or all sorts of things. So there's no single algorithm to use. But it is actually a very important feature, because when you look at the literature on classification of time series in astronomy, you find that, you know, many of the features are derived from an initial period found, particularly if you're doing something like a Fourier series decomposition and then looking at ratios of your amplitudes or phases to do classification. There's been some analysis that if you get the period wrong, then of course your classification rate is going to go to hell. You're going to be misclassifying everything. And there's also, J. Richards showed that 75% of all the time you're using to calculate these features in your thing are actually spent on using periodic features. So if you get that wrong, you're wasting 75% in your classification time. There are domain knowledge constraints as well. We use period as a single number, but we know from Kepler, and detailed studies of certain types of stars, R Lyrae are these things which are supposed to be single period, but we know that at least 30% of them have this Blaschko effect where they can switch periods. Or they show amplitude cycle-to-cycle modulations on long time scales, and as we get more and more decades of time series, this is going to be more important. There are objects which will change periods, which will have multi-periodicity or double periods, and a lot of our classifications just assume a single number for this. There are also questions about how trustworthy the periods in the literature are. Do we believe a period which was found or quoted on data which was taken 20 years ago without the sampling or the resolution that we currently have? And a lot of the thing is when we look at astronomical time series, we are dealing with still a large number of the vast majority of our time series have maybe a few hundred points, and then you get to something like Kepler where you have tens of thousands of data points, but there are fewer time series which have that resolution, but there are more coming. So we also did some work comparing those algorithms, and we had some surprising results. No algorithm is generally better than about 60%. There's no silver bullet algorithm for finding periods. What it turns out to be is it's dependent on the quality of your light curve, and it's also dependent on the type of object you're looking for. There are certain classes of repeating waveform which are better found by certain types of period finding algorithm than others. So you in some ways need to know what you're trying to find and measure the period of before you find which is the best period to apply to do so. And there are algorithms which are affected by irregular sampling and saturated values and performance constraints and that sort of thing. So, right, okay, so that's all I've got to say about periodic sources for the moment. Turns out, of course, that most astronomical time series are not periodic at all. They're aperiodic or stochastic. And there's a distinction between those. But, so there's a set of time series models called autoregressive models, which are gaining popularity in modeling of astronomical phenomena. So the first, most basic, let's assume we've got a purely random, so your time series is just some random process. So the simplest one is a random walk, where I'm just taking my previous time step and adding some sort of noise, and I can go off and do whatever. Then there are these autoregressive models. I think the laser pointer's just died on me. Oh, no, there we go. Autoregressive models where I can actually go have it dependent on further previous steps, modulated by some parameter, and so this is some sort of damped random walk. There are these moving average models where I can have sort of delayed versions of the noise terms coming in, and I can combine these into these so-called ARMA models. These are the autoregressive moving average models, and then there's a whole slew of family of where those become superfamilies of them. There's a lot of literature on modeling the stock market through these with successive degrees of belief. What's interesting about these, however, is if you take the power spectrum of these, these can give you different types of noise depending on what the slope of your the slope of the power spectrum is. So you can have red noise, pink noise, violet noise, white noise would be, of course, be a straight line. And what that means is that if you're looking for meaningful behavior, because you have this sort of correlated noise, there are then features in your time series which can be purely the result of the underlying process being a stochastic process, but which would look like something more significant than it may necessarily be. This is, so quasar variability is largely modeled as a damped random walk model, a first order autoregressive model, which is characterized by a variability amplitude and a characteristic time scale. So what you can do is you can fit that to a whole load of quasars, and you see that they occupy a particularly tight, well, relatively tight locus in time scale and an amplitude. And what you can then do is you can do the sort of question of, you know, are there outliers in that which are more interesting types of quasars? This is a good first order model, not brilliant. It has problems. One of the biggest problems it actually has is that this characteristic time scale, you need 10 times the baseline coverage of your time series to actually get an accurate estimate of that. So if you're looking at a phenomena which is maybe 300 days, and it's at a redshift of 1, so that means you need 600 days in the you need 6,000 days worth of data to recover that original number. So you need decadal baselines for that sort of thing. So it becomes problematic. So even though we can have really good models which describe the phenomena, just the complexity of recovering that can be difficult. Maybe we can go to higher order models to get better descriptions of our sort of things. This is damped random walk. This is the next model up. This is a second order model, which then introduces these peaks, or can have these peaks in the power spectrum, which of course introduces some notion of sort of quasi-periodic behavior. And so maybe we find sources where you sort of see this sort of periodic behavior, and it's supposed to be stochastic. And the problem then, you say, well, is this true periodicity or not? Because I know that this is not a white noise process, this is a red noise process. Am I just seeing correlated behavior here? Or do I actually have a genuine physical model where maybe I've got a pair of very close supermassive black holes, and what I'm seeing is modulation. So this is OJ287. This is 100 years worth of data. It peaks every 11 years. The idea is that there's a supermassive black hole binary, and the primary goes through the accretion disk every year, every 11 years rather. This is PG 1302. This has a baseline of about, this is 20 years worth of, this is 15 years worth of data, and the baseline here is about 5 years. But it has, again, this very, well, you know, looks periodic. You can go back 50 years and sort of have data which support it. Are we seeing periodicity here, or are we confusing different types of behavior because the analysis is not sophisticated enough, or we don't have enough data to sort of work with it? So it's problematic. A lot of the stuff, a lot of time series analysis has been built around discriminative processes. The idea, or discriminative statistics, the idea that I want to separate class 1 from class 2. And where we're moving now is more into these generative models where I can sort of get some idea of what the underlying population might look like in terms of some sort of statistical sense, and then that may allow me to do better explorations of the parameter space, or indeed do this sort of prediction stuff. Why do I want to do predictions? Because, I mean, if I got periodic behavior, it's trivial. But if I'm looking for the things that are interesting and I can monitor regularly, finding the behavior that is interesting as I'm monitoring is a lot easier in real time than just going through the archival, because I can then do real-time responses. And there are short-term behaviors that maybe, if I can catch it doing that, I can get straight on it and get a much better idea of what's going on. I mean, that's the whole basis of things like LIGO and transient astronomy. Now, the problem comes that, as I say, most astronomical sources are aperiodic. And there's a lot of effort in time series analysis, and well, if we can forecast the stock market, we can all get rich. If we can understand what climate change is, we can save the planet. If we can figure out earthquakes, we can make Southern California safe and epileptic seizures and whatnot. So there are a number of techniques that sort of show some degree of success for doing this. Localized chaos measure, so this is the stock market. This is one of these autoregressive models fit to it. But there's this model which is based on having ideas of deterministic, maybe it's a very complex nonlinear model underneath the stock market, and it gives me some prediction success. You can apply this to climate change, and that says that by the end of the century, we're going to be hitting 2.5 or 3 degrees worth of heating rather, which is not good. But there's a lot of effort in this sort of activity. Maybe we can apply these to astronomical time series and get better ideas. One of the things that Kiri was mentioning as well is this idea of deep modeling of time series, which is sort of where a lot of time series analysis is now going. With a regularly sampled time series, maybe you construct your feature space. So we put the time series into some sort of autoencoder network, and we can get features coming out. We can do prediction based on that, in the sense that we can sort of train on some part of the time series and maybe make a prediction about what the next chunk of it's going to be doing. And when we do that for things like quasars, what we find is, so we reduce our time series down to 16 features and then do a PCA of what that feature space looks like to get some idea of the sorts of things it's picking up. In terms of learning features from the data set, well, they're not particularly obvious, but you can see it's picking things that are going up and picking things that are going down and picking things that are dipping. So there's obviously sort of feature clustering and feature information in those time series which are related to the underlying physical processes that we believe are going on in those sources, and that these deep models might be able to be or more sensitive to. In fact, what we find is that when you look at prediction and fitting with the results of deep modeling versus the results of just fitting on a damped random walk model, the deep models do much better. So in summary, traditional time series analysis has looked at discriminative features, these very sort of simple statistical measures, into machine learning algorithms, and you do outlier detection based on Gaussian tails, and it has very little predictive power. The data volumes are now such that we can model individual sources in a much better way. We can capture full time series behavior through deep models, through featureless representations. We're getting better at identifying extreme, and we've got generative approaches. And the next generation surveys, these really large ones like LSST, and that CTF is sort of seeding, will enable real-time validation of predicted behaviors, so we can tie it back into the physical models and say, we expect that it might do this if we see this sort of thing. And then swift identification of deviance and getting other resources onto that, so to validate what we're getting. So I would say, let's go hunting for those techniques, and leave it there. Thanks.